Okay. So there's a change in volume. So the wire, it looks the same to us, but if you could look at how the atoms are arranged, there's a change in volume because they change in how they arrange themselves, right? One is more compact and one is less compact. And that's what is that change in volume, is that the atoms change their structure, right? So those are two different what we call phases, right? Phases are just different ways of organizing matter. So ice is a different phase than water because it's just organized differently. It's still water, it's still H2O molecules, right? But in one case, they're all bonded together in a specific structure, and in the other case, they're zooming around in a sort of lack of structure. We call that amorphous, right? Or liquids are by definition amorphous, right? So there's lots and lots of different phases. When we say solid, a solid is not a precise enough term for phases because there's lots of different types of phases that are all solids, right? For example, the phase of iron that's more expanded is one phase, and the one where it's more compact is just a different phase. And next chapter, we're going to learn the names of those phases and talk more about them. But for now, all I want you to know is that phases of matter are ways of arranging atoms. If you guys are all students or all atoms, then right now I'd say that you're a cubic lattice, right? I can see Vern here and Derek, Ryan, and Rachel are sort of like a cubic arrangement, but I could just as easily put them in like a hexagonal arrangement, right? And so there's cubic versus hexagonal, and there's lots and lots of other ones. So we'll talk about that next chapter, but for right now, it's just how things are arranged, okay? So let's start by considering our simplest scenario, which is a single component system like water, okay? What do we know about water? Well, we're gonna plot on our two axes. Remind myself which ones I plot them against. We're gonna plot temperature on the x-axis and pressure on the y-axis, right? So we've got temperature here, we've got pressure up there, okay? What do we know about water? Let's pick one pressure, 1 atmosphere, 1 ATM, right? So that's room pressure. That's where we live right now. Well, we're a little bit less up in the mountains, right? What do we know about changing the temperature? What does it do to the phases of water? Go to low temperatures, you get ice, right? So somewhere we know that down here we're going to get solid water, which is ice, right? Right? And then we heat it up a little bit, and we're going to cross over a point, right? And we're going to get liquid, water, right? And then if you keep on going, you're going to cross over another point, the boiling point, and it's going to be what? It's going to be vapor or gas, right? So solid, liquid, and gas. This is just for water, okay? It's just pure water. We haven't added anything to it yet, but just pure water. What about pressure, right? How does pressure change things? When you guys cook a cake at Los Angeles versus Salt Lake City, what do you have to do differently? Cooking a cake's probably not a great example. If you were to boil something, right? What happens when you boil water at Salt Lake versus Los Angeles? What's the difference? Where? Lower temperature where? Here. Why? Why does it boil at a lower temperature in Salt Lake City? It's true. It does. Yeah, you got to consider, think of the atmosphere as an ocean of gas molecules, right? If you're in Los Angeles, you're at the bottom of the ocean, so pressure is higher. Up here in the mountains, you're not as deep in the ocean of gas molecules, right? And so it's less pressure. Well, think pressure, all that is, it's just what's forcing the gas molecules in the liquid state from coming back out of the liquid and floating around the room, right? So if you're in Los Angeles, you've got more weight. It's not weight, it's pressure. You have more pressure of gas molecules pushing that water back in the boiling liquid. Therefore, you have to do it at a higher temperature for it to boil. And we're less here, right? So therefore, what do we change how do we change that? How do we draw lines for the different boundaries of solid, liquid, and gas for our phase diagram? I'm seeing this from Polly. That's exactly right. You're going to have something that looks like this, right? That's basically says higher pressure, higher temperature. We're pushing that transformation temperature up. The boiling point, we're pushing it up, right? As you increase pressure, you increase temperature. Now, what about the other one? It goes the other way. Have an idea why, Polly? Because chemistry. That's a great answer, right? It's really unusual, actually. It does something, I'm totally dramatizing it, but because it's a negative slope. I'm drawing it with a large negative slope. It's actually very, very, very small, but it's a negative slope, right? So that's really unusual. We'll talk about why that is. In fact, that's the reason why life exists on this planet. If that wasn't the case, the oceans would freeze over. They wouldn't have a film of ice. They would freeze completely. We'll talk about why, okay? So now we've got our very first phase diagram, right? And we've just drawn it by hand based off of what we've observed ourselves, right? But we basically know that, all right, high pressure, if you really press on something, you're going to get, generally speaking, you get solids. Ice is the exception, right? So most materials, just to clarify, most materials would have this curve, like that, meaning you'd go from a liquid to a solid if you add pressure. Ice is the unusual exception to that rule, okay? Erase that for now, okay? We know that if you go to high temperatures that you're generally going to get vapors, right? So this makes sense. So tell me, what would this point be? And how do we achieve it? Like, what's happening there? What that point is, basically below that point, as I go up in temperature, what am I doing? Yeah, Matt, what can you say about this?
So, that's the triple point, where it's the temperature and the pressure where all three of the phases can exist.
Yeah. So think of these lines I'm drawing. These are lines of equilibrium, right? The boiling point is just nothing other than the equilibrium between liquid on the left and vapor on the right, right? So same thing here. This triple point is at the equilibrium of all three of these what are called phases, right? Ice, liquid, and water. And steam. Ice, water, and steam. Solid, liquid, and gas, okay? So that means that there's some pressure, there exists a pressure at that triple point value, right? Where if you warm this thing up, you go directly from a solid to a gas without ever seeing a liquid. Where do we see examples of this? Dry ice, right? So dry ice, we know that it's got a diagram that looks not so different than this. The slope of that solid to liquid line is positive as opposed to negative. And we know that room pressure, 1 atmosphere, must be below that triple point, because at room pressure where we're at, it goes directly from a solid to a gas, right? So this all correlates to stuff that we have seen before and makes sense, I think, okay? So let's label some points on here. This is point B. We'll call this point A, point C, and out here we'll call that, out here D. Okay, so A, B, C, and D. So we already talked about some of these. Point B is just going to be our freezing point, or sometimes called melting point. Same thing, it's just which way you're going, right? Point C is going to be our boiling point. I guess you could call it condensation point, but people only call it the boiling point, right? Point A, Matt said that's called our triple point. Point C, okay? So we can now that we've got these things labeled, we can introduce the first concept in this chapter. Oh yeah, go ahead, Callie.
So I was just saying, like, if you put ice in a vacuum, it would just sublimate?
Yeah, that's what a freeze dryer is. Those freeze drying systems that are getting kind of popular now among kooky people that think the world's going to end, like because they cost a lot. They're like $3,000 for a freeze dryer. But you can take your steak and eggs, hot, prepared, ready to go, throw it in the freeze dryer, and turn it into like Richmore camping style, like freeze dried bacon and eggs, right? Or whatever I said, right? It'll actually preserve it pretty well, because why food gets ruined is when you freeze it, you go from solid to liquid, right? And that's a problem because it like expands, and that expansion makes things like tomatoes explode and terrible things, right? So, and then it goes the other way when you start out as a solid, right? If you got a frozen tomato and you take it back, it has to go through that liquid phase first. So it's just not great, right? So freeze drying prevents that. You freeze something, so what do you have to do? You have to lower the temperature first, right? And then you lower the pressure, right? Then you can take it up there and you can avoid the transformation to a liquid. Or vice versa, if you want to go the other way. You can avoid liquid by going down in pressure first and then freezing it. That's what they do with freeze dryers. They go down in pressure from where you're at, turn that liquid into a vapor, basically, right? Right? And get rid of it. So freeze dryers are awesome. We like freeze dryers. And you can explain them with diagrams like this, okay? So let's talk about Gibbs phase rule. Gibbs phase rule is the first sort of equation we're going to see in chapter 10. Yeah, Matt?
So what was point D?
We'll talk about it in just a second. I'm going to use, for an example, Gibbs phase rule.
Okay.
It's not a point. It doesn't have a name, but we're going to use it. So the Gibbs phase rule is a rule. The first thing to remember, it is only to be used at equilibrium. And these phase diagrams are only for equilibrium, meaning if you let it sit long enough and things totally even out and reach equilibrium, right? It doesn't take into account kinetics. You have to modify these when you talk about kinetics. We'll do that maybe later. It says the following. It says P plus F equals C plus N. Well, what is P, F, C, and N? P is the number of phases present. F is the number of external variables, sometimes called the degrees of freedom, needed to completely define the state of your system. C is the number of components, and N is the number of non-compositional variables. So let's go back to our 4 points, B, C, A, and D. At point B, remember we're going to do, turn on draw. What's happening? That's really unusual. Strange. That's odd. Okay, that's not working. Bizarre. Okay, let's type it out. What happens at point B? How many phases are present? Remember, it's going to be P plus F equals C plus N, right? So how many phases do we have at point B? Oh, you know what? If I add lines, it's going to make bad things happen later. We have 2, right? Is this really not going to draw? What have I done wrong? Okay, we've got 2. I'll have to write it to the side because I can't go down without messing up the notes later on. Right, so we've got 2 phases, okay? Technology strikes in the middle of class. Okay, degrees of freedom is what we're going to ask in a moment. We want to know what is degrees of freedom, meaning how many things can we change without messing up the equilibrium, okay? C is the number of components. How many components do we have in this phase diagram? We have 1 component. It's just water, right? There's different phases, but there's 1 component. And then N is the number of non-compositional variables. How many non-compositional variables do we have in this phase diagrams? We've got 2. We've got pressure and temperature. Try closing this real quick. Okay, so there's 2. So if we write that equation, we've got 2 plus F equals 1 plus 2. Maybe it'll work. Cross our fingers. Nope. Don't know why. Can I draw with touch? 2 plus F equals 1 plus 2. All right, that's the most kindergarten thing I've ever done in my life. But 2 plus F equals 1 plus 2. Oh, the pen's not working. Right, so therefore F is what? What does that mean? It means I can change one variable. I can change one variable, but if I want to maintain the same equilibrium, I can't change more than one variable. Well, where do we see evidence of that? Let's say I change pressure. I elect to change pressure on this diagram, so I go up in pressure maybe. If I want to have equilibrium between solid and liquid, it changes my temperature over to this point, right? I can't choose both. If I choose to change temperature by moving over, it says you've got to move down in pressure, right? So that's just degrees of freedom, okay? So if we do it at point C, what do we have? At point C, it's the same thing. We've got 2 phases. So again, we only have 1 variable, right? We're going to move along this line. What about at point A, the triple point? How many phases are present at the triple point? We've got all 3 phases, solid, liquid, and gas, right? So P equals 3. F equals what? Bizarre. What if the battery died? So F is, we're going to find out what F is. What is N and C and N? C and N is still the same. It's just 1 and 2, right? Therefore, F can be equal to what? 0. We have no degrees of freedom. We can't change anything and maintain equilibrium. Make sense? Because where can we go in this diagram and have all 3 phases in equilibrium, okay? So this is Gibbs phase rule, okay? What about at point D? At point D out here, how many phases are present? We've got 1 phase, so now it's 1 plus F equals 1 plus 2. F is then equal to 2, meaning we can change 2 variables and have still pure gas, meaning we can go down in pressure, down in temperature, and we might still be right here, still having a gas. Fair enough? Any questions on this Gibbs phase rule? Yeah, Alex?
I'm not quite tracking on your different variables. So F is the degrees of freedom.
F is our degrees of freedom, meaning things we can change while maintaining equilibrium.
Okay.
P is the number of phases present in that equilibrium.
Okay.
Also the ratio of them. We'll come back to that in a bit. And then we've got C and N. C is the number of components. This is a single component phase diagram right now. It's just pure water. Soon we're going to make a new one. We're going to say water plus Kool-Aid, right? Plus Kool-Aid powder. It's going to change it to now 2 components. And then, let's see, N is, C plus N is the number of non-compositional variables. In this case, we can change pressure and temperature. Okay, any questions on this? Yeah, Kylie?
So it says equilibrium, that basically it's the same as that. So like if you're at point B and you want to change a variable, you would have to follow this line.
Yeah, if you want to maintain a mixture of liquid and water, you got to stay on that line is what it's saying. So if you choose to change something, it picks the other thing in this system, right? And it says in some cases, like point A, you can't change anything if you want to maintain equilibrium between 3 phases. Because where on this diagram can you find all 3 phases in equilibrium? Only at point A. So you can't change anything. You have no degrees of freedom. Okay? Any other questions about this? Okay, clicker. Let me fire up the clicker. Oh, we already did this, so this will be free points. All right. We did this together. Okay, that is the ID number. This is the receiver number. Pick our class. 10-1. That will show up. I gotta close this. Okay, now it should pop up. So the very first question, again, we did these. That's tiny. Guys, the struggle is real today. I just switched back to my old laptop and it's causing me grief. I apologize for this. I will get this fixed before next class. There's our phase diagram. It's the one we've just been looking at. Nothing different, right? So it's saying how many degrees of freedom at point A? Is it 0, 1, 2, or 3? We just talked about this. At point A. So your channel, oh gosh. I don't even know how to get out of this now. This is going flawlessly. Huh. Okay, channel 41, session ID, right there. I will just read it to you. At point A, type in A. So the first question, the answer is A. We already did this. If you were here, you will get credit if you type in A for this first one. Okay, everybody good? Yeah, Matt?
So if point B on this one is condenses to supercritical fluids, is that like plasmas and stuff?
We will talk about supercritical fluids only briefly in this class. We will not go into depth in it. A supercritical fluid, you can think of it like when you heat a liquid up. Good. When you heat it up so much that it starts behaving like a gas and the distinction becomes really blurry, that's a supercritical fluid. We won't talk about it in this class. Okay, at point B and C, the answer is 2. Type in C. Get your points for being here today. Sorry, 1. 1. Type in B. Sorry, I almost led you all astray. Type in B. Get your points. I forgot that we were doing this as a clicker example. I apologize. That one's on me, 1% person. That one's on me. And then the last one at point E, what would this one be? Point E is out in the middle of the gas field. Do we have 0, 1, 2, or 3 degrees? 0 would be A, 1 would be B, 2 would be C, 3 would be D. So, C. Okay. Sorry, I did our example. Forgot about it. Okay, everyone good? Points achieved for the day. We're good. Okay, back to the work. Okay, so we're going to come back to Gibbs phase rule in a bit when we get to multi-component systems, harder diagrams. But let's now ask the question, how do we get this phase diagram in the first place, right? Here's what the actual phase diagram for water, H2O, looks like. Like I said, this slope is barely negative. It's not strongly negative. It's barely negative. Plus, there's all this stuff. What on earth is going on up here? It's blue, which means it's solid. And there's like 11 of them. There's 11 different phases of solids of ice, right? Anybody knew this? Last year we had a student in my class who was an avalanche expert, like he makes videos on this, and he was desperate to go up on the mountains with me and talk about the phases of ice, because it has all to do with whether or not avalanches happen. It's not just the phase, but it's the microstructure, how these phases come together and look, apparently. But there's lots and lots of different phases, right? And just like with water, most materials have more than one solid phase, especially when you start to go into crazy pressures like 100 gigapascals. That's like bananas pressure, right? That's really high. We're never going to see that almost ever, right? So most materials have multiple phases present, like iron. Iron clearly has 2. We saw evidence of it because the wire did something weird in terms of expansion, okay? So where did this diagram come from? What do you guys think? Anybody have a thought? Experimental data. So basically somebody took a vessel, right? They changed the temperature or the pressure, and they sort of peeked inside of it and said, yep, looks frozen, sort of thing. Okay? That's one way. That was like early on days of phase diagrams. How could we be more exact about it? What do you think, Alex?
They probably started diagramming like molecular forces and what the lowest energy states were.
Bingo. That's exactly what they do now. It's computed. They take our free energy that we just learned last chapter, huzzah, and they use it for something. Terrific, right? They say, what happens? Thermodynamically speaking, that's at equilibrium, the one that lowers the energy the most. So they say, well, what are the different types of structures that could form? They calculate the free energy for them. They see which one's the lowest. Voila, you end up with a phase diagram. You have the phases as a function of pressure and temperature where the most stable phase is present, right? There's lots of other experimental ways, which we will probably not talk about in depth in this class, where they get these things and they use those to calibrate calculations. But nowadays, yeah, they calculate these things from thermodynamic data. Things like entropy and enthalpy, things that you're like, we'll never use this ever. They use it. They make these great diagrams, which we can use to know when avalanches will happen and stuff. Like, it's actually pretty useful stuff. Okay, so they calculate, it's exactly right. They use Gibbs free energy because it's the lowest free energy, right? So we remember this, that G equals H minus TS, right? So we can now plot G versus T and P. I'm not gonna be able to. And it's back. I'll take it. I'm not gonna question why Microsoft bestowed upon me the ability to write again. I will just take it. G versus T and G versus P. Okay? We're going to plot G versus T and G versus P for these three phases. Let's do it for, which one do we do later? If ice floats, how it so let's do it for benzene. Let's do it for a normal material, something that doesn't have that weird negative slope. So normal material, something like benzene, alcohol, right? One of these things. What will happen if we plot G versus T? Well, we need to know what G versus T looks like for the different phases present, solid, liquid, and gas. So what is dG dt? That's going to be the slope, right? I'm going to draw a slope here of some lines for our three different phases. Well, what should dG dt be? Look at our equation. What should it be? It should equal, if you take the derivative of that energy expression, it should be negative S. So the slope is what we're saying should be proportional to negative entropy, right? Fair enough? We all agree about that? And then pressure, same thing. If you remember that H equals U plus PV, now you have P, you can say that the slope of dGdP must be what? Somebody? Just volume, right? Volume. If you take the partial derivative right there with P, you just get volume. So that's great. We can just draw lines, and the lines are going to be sketches, right? These are not plotting, we're just sketching. But we can sketch solid, liquid, and gas, and we can sort of get a feel for where these things come from, right? So let's do it. Let's say solid, liquid, and gas. Tell me about the entropy of these three phases, solid versus liquid versus gas. Let me actually write these in different colors for, I don't want to make it angry. I'm not going to mess with it. It doesn't want to erase. I'm just going to leave it.
Entropy is lowest for solid.
Entropy is lowest for the solid, right? Lowest. And then what's it highest for? Gas, right? Okay, let's go over now. What about volume? Generally speaking, not for water, generally speaking, what has the highest volume, solid, liquid, or gas? Gas is going to be highest volume. Liquid will be somewhere in between, and then this will generally be the lowest. Ice floats because it expands when it solidifies. That's the unusual part, right? But this is not for ice. This is for a regular material, okay? Everybody agree with this so far? So now we can draw these lines. So let's say that solid is red. Please work. Liquid is blue. Gas is green, okay? Right? So we're going to say that dGdt, the slope that we're going to draw of these things, is going to be proportional to the entropy. And then we're going to make it a negative slope because it's a negative sign, right? So the one that has the highest slope should be gas. We all agree? Right? So we're going to take our gas, green, and we're going to draw it right there. Okay? Highest slope. Then we're going to draw a liquid. It's going to have slightly less slope. Finally, we get to our solid. Oh, I already messed up. Sorry, gang. That's not right either. Guys, technology is getting me down today. I apologize. Okay, and there's solid, right? That should technically still be negative. I just sketched it poorly. Sarai is looking at me, or Ashley's looking at me like that's not going to do. All right, Sarai. There we go. We good? Approved. Okay, so we've got, again, this is solid, liquid, and gas. We almost had it. Okay, so what? Why do we care about this? Is this useful at all to us? It is. We can say that this stuff, this basically says what's lowest in energy, so G, which one of these lines is lowest at a given temperature, right? At a given temperature, we can say that solid is our lowest free energy phase, right? And then there's a region here, we switch to black, there's a region where, so this is solid, is favorable. Here we've got liquid as lowest, and over here we've got gas as lowest. So if we go back to our diagram, we can see that. Let's go to the one that we drew, it'll be easier to see, right? Where do we go from solid to liquid to gas? Well, right here, at room temperature, right? Right? So we sketched it for this room pressure. It's not room temperature, room pressure, right? It went from solid to liquid to gas as we increased temperature, right? So I could ask you to redraw this G versus T at a different pressure. What if I asked you to draw it below the triple point? How would we draw it differently, right? Right here, right? Below triple point. If we wanted to draw it below the triple point, how would it look differently? Well, it's G versus T, just like before. If we go up to our diagram, what happens? If you're below this pressure, so we're somewhere in this region right here, right? We're below the triple point. As you warm it up, it goes from ice to gas, and liquid is never present, right? Therefore, it must never be the lowest phase. So how do we draw it? Any guesses? Goes from solid straight to gas. What do we do? So let's start by just drawing the solid line like before. There's our solid line, okay? Here's our gas, right? This temperature would be what temperature? It would be whatever the temperature is where it crosses this line at, okay? That's the point where it goes from a solid to a gas. So where's liquid at? Any guesses? Where should we draw liquid? Higher. It's got to have the same slope. It's got to have the right slope that we talked about before, except now we're going to draw it up higher. There, liquid, right? So at no point is liquid the lowest energy phase. Any questions about this? So people that do calculations and calculate thermodynamic phase diagrams, all they have to do is come up with free energy expressions, right? And then know what the entropy is of these systems, and they can start seeing, okay, the entropy changes in such and such a way, it's going to modify our phase diagram by just making plots like this and getting points, and then connecting the dots, basically. Let's do a few more examples. Right? How about G versus P? This time we're going to fix temperature, right? We're going to hold temperature constant, but we're going to change pressure. What should it do? It should be proportional to the volume, right? So let's say volume is going to be, of gas is going to be our highest, right? Then liquid, and then a solid, right? So again, this basically says as you increase pressure, we should be seeing, at least at the temperature where this happens at, you should see it go from gas to liquid to solid as you increase pressure. Do we see that in our phase diagram? Yeah, you betcha we do. We go from, again, this is for normal materials, it'd go from gas to liquid to solid. It would cross that dashed red line. For liquid, it doesn't work. Liquid water has that funny slope, so it doesn't work. Most materials, that would work, okay? So does this make sense? Are you guys catching how these things relate to one another? The concept I want you to take away with, what I would ask you on a test is, I'd say, sketch a G versus T or a G versus P at a given temperature. Maybe I'd give you this phase diagram, and I'd say, ignore the other phases of ice, assume there's just one solid phase, right? Sketch G versus P at this pressure, or G versus T, sorry, at that pressure, right? And you'd say, great, at that pressure, at 100 pascals, if I sketch G versus T, I know that it goes from a solid to a gas, right? Right? And we know that G versus T is proportional to the negative entropy. So it's just going to be exactly what we drew before. You're going to say, all right, my solid must go like that. My gas must go like that. Right? There's our boundary when it switches over. Liquid must be up somewhere higher. Right? So I'll ask you to draw something like that on the first exam. Any questions on this? You will have a homework where you'll get to practice it. Yeah, Kylie?
Can you just go back to the what we were saying?
G versus P.
Okay.
So let's do another one, G versus P. Let's do it for right here, right? Let's say we're at this point, okay? That's for water. So we're going to do the water system, right? How would we draw it? Let's do that. So how would it look differently for water? Let's erase that. For water, how would it look differently? So I want you guys to, with a partner, sketch such that, let me draw it so it's clearer. You're gonna sketch it for that temperature where it goes right there, okay? So turn to your neighbor and you're gonna sketch G versus P for that temperature. Just to the left of the triple point. Just to the left. Can you see this? Is this can you not see it? Should I draw it one more time? So I want you to draw it right here. Okay, good? So with your neighbor, sketch that real quick. So you start with a big, you're going to turn into a solid. And at high enough pressure, you're going to go to So we're plotting G versus P, and remember, for water, it breaks the rule. Solid is a larger volume than liquid. That's not normally the case. For water, it is. So that'll tell you the slope, what the slope needs to be. Okay, so sketch that. Give you 2 more minutes. Actually, we're out of time, so we'll pick up here next time. How about that?
I wrote down like my slope for, I think it's number 2. I wrote down like the y equals whatever, x plus. I didn't include the graph. I have all the information.
You can find it at it.
I would have to print it, I can send it to someone.
Why don't you print it and email it to me and
All right,
I'll
sounds
print it
good.
out for you. Yeah.
I just had a question. I'd always feel like I was taught once that the reason ice expands is because the traps inside of it. Whereas, no, it's actually
Fundamentally, even if it's pore-free, the reason why it has to do with there's stronger bonds.
okay.
But it's stronger bonding, but it's the crystal structure. So I can't answer that until next chapter. Next chapter, it has to do with crystal structure. Yeah, Gibbs.
So, can you explain why
I can't, but my TAs can't. They have a rubric to explain it. So Josh graded Josh and Dave. So send Josh and Dave an email, and they're happy to get together and explain it.
Okay, cool.
Okay, great.
So, is this how they get like liquid oxygen for like aerospace stuff?
Exactly. You look at the diagram and say it's by pressure. Just like compressed gas when you like spray your computer cleaner, they just pressurize it, it goes to liquid form, and then thermodynamically it wants to go up to liquid or gas phase when you release that pressure, and so it does when you press that button, it sprays.
That's what they can get to go.
And that's something else. That's but yeah. What's up? Question on homework?
No, this is great. I if not, that's fine. I'll take this.
Yeah. Get it today if you can, but as quickly as possible because I want to post the solution soon.
Okay, I just.
Okay.
Is there any time?
Yeah, no problem.